Hey class, in today's lesson we're going to talk about inverse functions, which is found in section 1.5. Our objectives are to find inverse functions informally and verify that two functions are inverses of each other, to use graphs of functions to decide whether functions have inverses, and to find inverse functions algebraically. All right, so an inverse function. So a function can be represented by a set of ordered pairs. By interchanging the first and second coordinates of these ordered pairs, you can form the inverse function of f, which is denoted by f of, or f to the negative 1. And really we just call it the inverse of f. If we see this notation at the end, we just call it the inverse of f. So our first example says, find the inverse of f of x equals 4x, then verify that both f of the inverse of f of x and the inverse of the f of x are equal to the identity function. So we were talking about this earlier, actually in our last section 1.4, which was composition of functions. And what you're going to see is technically if inverses, if a function and its inverse can compose within itself and they equal x, then they are technically considered true inverses. So here we go. So to find an inverse, we write our function first. And then instead of using function notation, we go back to regular old x and y. And then we switch our x and y variable to become x equals 4y. And then we continue solving for y. This will then give us y equal to x over 4, or the inverse of f of x is x over 4. So here's the inverse and here's the original. So we're going to compose them into one another. So if I do f of the inverse of f of x, I'm going to put the inverse into my function. So that will be 4 times x over 4. Well, the 4's will cancel to give me just x. That's what I wanted. Now I'm going to do the inverse of f of x. So in the inverse function, I'm going to put my function. So on the top, I'm going to put 4x, and this is over 4. Again, my 4's cancel to give me x, and that is what I wanted. So this is our way of verifying. Now, usually what will happen in a situation like this where you'd want to do this is you have two functions, and so algebraically you could compose them into one another to see if they both equal x, and if that's the case, then you know that they're inverses. So we're going to try it again. So again, f of x equals x minus 6. We're going to write it in standard formation, and then we're going to switch our x and y to get x equals y minus 6. Now again, we solve for y, and we're going to get y equal to x plus 6, but we know that's not y. That's really the inverse of f of x equal to x plus 6. Okay, now we're going to take those two functions and we're going to compose them into one another. So if I do f of the inverse of f of x, sorry guys, my pen is a little off. That would give me, putting the inverse is down here, into my function, that would give me x plus 6 and then minus 6. Again, x plus 6 minus 6, the 6's will cancel to give me just x. That's what I wanted. Now if I do the inverse of f of x, that would mean that I need to put the function into my inverse. So in the front, I'm going to have x minus 6, and then I need to continue by adding 6, which is the same thing as x minus 6 plus 6. Again, those cancel to give me x. So again, they are inverses of one another. In example 2, we are going to verify that these functions algebraically are inverses of one another. And essentially, it's a lot like what we just did. We could compose them into one another. So that's what we're going to do. So we're going to do f of g of x. And then we'll go back and later do g of f of x. So if I put g of x into f, that means it'll be 2 parentheses, the cube root of x plus 1 over 2, and then minus 1. Okay, what's going to happen to us first? Oh, and this was cubed, sorry. Okay, so cubed and cube root are going to cancel. So that will leave us with 2 times the square root, not anymore. It's 2 times x plus 1 over 2, and then it's still minus 1. Now, since I'm multiplying, my 2 and my half cancel, and that leaves me with x plus 1 minus 1, and then again, the 1's will cancel to give me x. So that's what I wanted. Let's check to see if that happens on the other side. So if I put g of f of x, that means I'm putting my f function into g. So that would be the cube root of where my x goes. This is 2x cubed minus 1, and then it's still plus 1 in the numerator divided by 2. All right, so within the function, what I see is that the plus 1 and the minus 1 are going to go away. So essentially this is the cube root of 2x cubed over 2. The 2's cancel, so essentially this is the cube root of x cubed, and the cube root of anything cubed is itself. So in this case, again, it's x, and that's what we wanted. So again, now this time, actually without doing all of the work, what we will do is we will just compose f of x into g of x. And if they are inverses of one another, they should work, okay? So let's test f of g of x. So f of g of x, wrong notation. Again, that means g goes into f. So that'd be 5 over x minus 2 over 5. And then we still have to finish minus 2, okay? Essentially, what that is going to do is if I got a common denominator, with the 1 and the 5, that means I have to multiply this by 5 over 5. Actually, let me go back and use a different color. So again, that means I would have to multiply this by 5 over 5 to get 5 over x minus 2 over 5 minus 10 over 5, which is essentially 5 over x minus 2 minus 10 over 5, which is really 5 over x minus 12 over 5. This is really 5 divided by x minus 12 over 5. When you divide fractions, essentially you multiply by the reciprocal to get 5 over 1 times 5 over x minus 12. So really this is going to give us 25 over x minus 12. That's not x, okay? So I already know that g of x is not an inverse. So I'm going to go ahead and erase this so that I can check to see if h of x works. So g of x again does not work. I have some stray marks left over, but we're just gonna go with it. All right, so next function. So I said we're gonna go ahead and test, oh, that looks trashy. All right, we're gonna do f of h of x, which means I'm going to have 5 over h of x, which would be 5 over x plus 2, and then we still have to finish it with the minus 2. Well, now this looks a lot better because the 2's will cancel there. That's highlighter, oops. The 2's will cancel. And so we're left with 5 over x. And essentially what that means is this is 5 divided by 5 over x. Again, you flip the reciprocal or flip the fraction, which is the reciprocal, to give you 5 over 1 times x over 5. The 5's cancel, you're left with x. So this is a function. I'm going to show you one more thing. There, and actually it's going to come up just a tad bit later, so let me not skip ahead. So here we go. Let's keep going. All right, so the graph of an inverse. The graphs of f and the inverse of f are related to each other in the following way. If the point AB lies on the graph of f, then the point BA lies on the graph of the inverse of f, and vice versa. This means that the graph of the inverse of f is a reflection of the graph of f in the line y equals x. That's why we always get x as an answer when we're composing, because these two functions compose within each other around the y equals x function. Okay, so essentially if I just switch their ordered pairs, they should be inverses of one another. So as an example, what we're going to do is we are going to verify graphically and numerically that these are inverses of one another. So I actually don't have a great way of showing you on a graph, so I'm just going to sketch what 2x cubed will look like. So 2x cubed essentially will be a cubic function that's been stretched by a factor 2 and shifted down 1. So let's just say it looks like that. Okay, you should verify this on your calculator. And again, the cube root of x plus 1, so this is the f of x function. The cube root of x plus 1 over 2, which is the g of x function, I'm going to switch colors, essentially looks like this. Okay, that is g of x. And so I can tell graphically, if I were to do this graphically, that they are inverses of one another because they reflect across the y equals x, which is my blue dotted line that I just did. Numerically, that would just be that you would look at your x and y values, which we won't worry about. I just want to let you know what it looks like graphically. But if you wanted to know, you'll see the table in an example or two. Okay, so I thought it was the next example, or the next few examples, but it actually is the next one. So it says the existence on an inverse function. So the function does not have to have an inverse function. For example, f of x equals x squared has no inverse, and this can be shown in the tables above. So if you look at our first table, which is right here, remember I mentioned, if something is a function, if x does not go to more than one y. So all of these are very much different x's, and they're going to different numbers. So this one, the top function, which is our regular f of x equals x squared, it is a function. However, what if we were to just, because in order for us to so-called say that something is an inverse, that means we are switching our input and our output values, right? So, but what you notice here in the reverse, I will call, because it's not necessarily the inverse, but the reverse, you'll notice that you have two different, the same inputs, but they're going to two different outputs. So what would be considered as inverse is actually not a function. So it is possible for a function not to have not to have an inverse that is a function. It may have an inverse, but that doesn't make it an inverse function, is what I'm trying to say. And those that are, so a function and an inverse function, if a function has an inverse function, we call that one-to-one, okay? We call that one-to-one. To continue, it says to have an increase or an inverse, a function must be one-to-one, which means that no two elements in the domain of f correspond to the same element in the range of f. To check graphically, which is the best way to check graphically if a function will have an inverse, you use a horizontal line test in the graph, and if the graph intersects a line more than once, it does not have an inverse. So remember, we use the vertical line test to see if the function, or to see if a graph is a function, or to see if a line is a function. And then now we're using the horizontal line test to see if that same original function is also a one-to-one, meaning that it will have an inverse. All right, so it says, is the function below one-to-one? So just as a sketch, because I know what the sketch resembles. That's terrible. Sorry, that was supposed to be a straight line. It is a square root function that has been shifted up 1. So to sketch it, that function should look something like that. Okay. Now, first of all, this is a function because it passes the vertical line test. All right. It does not intersect in more than one spot. And it is also a inverse because it also passes the horizontal line test. It may look like in this section right here that it's actually a straight line, but it's not. Okay, so this does pass the horizontal line test. So yes, this is a one-to-one. All right, so with example 5, we're gonna find the inverse of a function and if it exists. Okay, so to just find the inverse, again, it's just like what we were doing before. Our function is already written, so we're gonna switch this to y equals 5 minus 3x over 2, and we're gonna switch our x and our y variable. Okay, so that will now be x equals 5 minus 3y over 2. Our goal is to get y by itself, so here we go. We're gonna start by multiplying by 2 on both sides. So that was 2 and 2. 2's are gone. We're left with 2x equal to 5 minus 3y. All right, then the next step is to continue to get y by itself. So we're going to subtract 5. So we're left with 2x minus 5 equal to negative 3y. All right, then our last step will be to divide by negative 3 to everything. So that means that y will equal 2x minus 5 over negative 3, or that the inverse of f is equal to 2x minus 5 over negative 3. Okay, and then if you want to check to see if it is one-to-one, we would go then further to type that in our calculator and just double check what, the horizontal line function. Actually, we would do the horizontal line function with the original. One more. All right, so again, we're going to find the inverse, and then we're going to sketch this one this time. So again, we're going to switch it. So the original says y equals the square root of 2x minus 3. Okay, we're going to switch x and y. So then we're going to get x equals the square root of 2y minus 3. All right, so to get that by itself, we need to square both sides. So you're going to get x squared equal to 2y minus 3 because the squareds cancel with the square root. Again, then we're going to add 3 to both sides. So we can continue to get y by itself. So now we have x squared plus 3 equal to 2y. Finally, we're going to divide by 2. And so our final answer should be y equals x squared plus 3 over 2, or the inverse of f equals x squared plus 3 over 2. All right, the graphs of these, So the original is just, and again, these are just sketches. The original, it kind of goes up like that. It shouldn't be right on the 2. It's actually at 1.5. But anyways, that's the sketch of the first one, and then the sketch of the second is actually again right at that 1.5. And so again, I can tell vertically, not vertically, but graphically, that they're going to pass the horizontal, that they are inverses of one another because they reflect over the y equals x function. All right, guys, we are done with this video. If you have any questions, please come see me for tutoring.